Alright, let's go. Number 10. The last star that will ever form. Gregory Laughlin was not trying to date the end of anything. In the mid-1990s, he was running stellar evolution code on very low-mass stars, routine housekeeping, the kind of modeling that checks whether a 0.1 solar mass object burns hydrogen the way the textbooks claim it does. He set the simulation running. It kept running. The star refused to die on any timescale the code had been written to handle. The accepted picture of the galaxy is a cycle, and it is a good one. Gas clouds collapse under their own weight. Stars ignite, fuse, exhaust themselves, and return their processed material to the interstellar medium, where it cools, collapses, and lights up again. The sun is a late-generation product of that loop. Every atom of calcium in your teeth passed through it. The loop is supposed to keep turning. The loop is winding down. It has been winding down for 10 billion years. Nobody noticed until the deep surveys came in and stacked the data by redshift. The peak is behind us, far behind us. Pietro Maddow and Mark Dickinson, in their 2014 review in the Annual Review of Astronomy and Astrophysics, assembled the cosmic star formation history and found the rate peaked around redshift 2, roughly 10 billion years ago, and has since fallen by about a factor of 30. David Sobral and the Hizzles survey team, writing in monthly notices of the Royal Astronomical Society in 2013, extrapolated that decline and concluded that, if it holds, something near 95% of all the stars that will ever exist have already been born. Fred Adams and Gregory Laughlin, in their 1997 review in Reviews of Modern Physics, put the end of the star-forming era at around 10 to the 14 years. Every proposed reprieve runs out. Recycled gas from stellar winds sounds promising until you follow the accounting. Most of it ends up locked permanently inside white dwarfs, neutron stars, and black holes, which return nothing. Fresh infall from the cosmic web fails because accelerating expansion strips galaxies of their supply lines. Brown dwarf collisions can build new hydrogen-burning stars. And Adams and Laughlin calculated the rate, a handful per galaxy across timescales approaching 10 to the 15 years, each one dim and short by comparison. Pristine primordial gas is already contaminated with metals. Nothing restarts the era, everything only stretches the ending. Which means the sky is a temporary condition. Every night sky in the whole of human history, every constellation any culture ever named, every star anyone has ever wished on, belongs to a brief lit window inside a cosmos that will spend essentially all of its existence dark and empty. You were born during the lights-on phase. Nothing guaranteed that. If observers can only exist while the stars are burning, and the burning is a rounding error in cosmic time, what exactly are we a sample of? Running out of fuel is one thing. Running out of matter is something else. Number 9. The proton that might not be permanent. Howard Georgi and Sheldon Glashow were not hunting for a doomsday mechanism. In 1974, working at Harvard, they were chasing elegance, trying to fold the strong, weak, and electromagnetic forces into a single symmetry group so that 3 separate coupling constants would collapse into one. The theory worked. Then they looked at what it implied for ordinary matter and found something they had not gone looking for. Baryon number conservation is one of the quietest assumptions in physics. Protons are stable. No experiment has ever caught one falling apart. In the standard model, this stability isn't a fundamental law at all. It emerges accidentally, because there simply isn't any allowed interaction that converts a quark into a lepton. The proton has nowhere to go. So it stays. Unification opens a door. SU requires new force carriers, the X and Y bosons, and those bosons connect quarks to leptons directly. A quark inside a proton can turn into a positron. The proton comes apart. And the theory gave a number. Georgi and Glashow's 1974 paper in Physical Review Letters implied a proton lifetime near 10 to the 31 years. Enormous, but testable, because a large enough tank of water contains enough protons that a few should decay every year. The IM detector built in a salt mine under Lake Erie, and Kamio Kande in a Japanese zinc mine went looking through the 1980s. They saw nothing. Super Kamiokande, 50,000 tons of ultra-pure water washed by more than 11,000 photomultiplier tubes, has now pushed the limit on the decay channel to a positron and a neutral pion past 2.4 times 10 to the 34 years, 1,000-fold beyond the original prediction. The minimal theory is dead. What replaced it is a parade of models that survive by becoming harder to test. Supersymmetric SU raised the lifetime but predicted a different channel, Proton Decay and antineutrino, which Super Kamiokande has also failed to find. So models fit anything, because they carry enough free parameters to be tuned to any lifetime you like, which is another way of saying they predict nothing. Flipped SU and extra-dimensional constructions suppress decay by separating quark and lepton wave functions in space, an arrangement inserted by hand. And none of these can be abandoned, because Andrei Sakharov showed in 1967 that producing a universe with more matter than antimatter requires baryon number violations somewhere. The excess matter you are made of is evidence that the rule breaks. Follow that through to your own body. If the proton has a finite lifetime, then the hydrogen in every water molecule in you is sitting on a clock, and so is every atom in every object you have ever touched. Permanence becomes a statistic with an expiry attached. Either the matter you are built from has an expiration date nobody has measured, or the universe broke its own rule to build you. Which is it? Matter surviving is one problem. What eats it is another. Number 8. The black hole era and the long evaporation. Stephen Hawking set out to prove Jacob Bekenstein wrong. In 1973, Bekenstein had argued that black holes carry entropy proportional to their surface area, and Hawking found the claim absurd. Entropy implies temperature, temperature implies thermal radiation, and a black hole by definition cannot radiate. He ran the quantum field theory calculation in curved spacetime specifically to kill the idea. The calculation refused to cooperate. The classical picture is absolute. The event horizon is a one-way surface. Cross it and no signal, no particle, no information ever returns. Black holes can grow by swallowing and merge with each other. And that is the complete list of things they do. They are permanent. In general relativity, they are the closest thing the universe has to a final state. Hawking's math produced a spectrum. Not a trickle of leaked debris, a clean thermal blackbody, exactly what a hot object emits. He spent months hunting for the error. There was no error. The result appeared in Nature in 1974 under the title Black Hole Explosions. Don Page then worked out the actual rates in Physical Review D in 1976, and the numbers are strange in both directions. A black hole 1 solar mass across takes roughly 10 to the 67 years to evaporate. A supermassive 1 of 100 billion solar masses takes about 10 to the 100. But a solar mass hole has a Hawking temperature of 6 times 10 to the minus 8 Kelvin, and the cosmic microwave background is currently 2.7 Kelvin, so today every black hole absorbs far more than it emits. None of them can even begin dying until the universe cools below their temperature, which takes a few 100 billion years. Then the harder problem starts, and it has stayed unsolved for 50 years. Hawking argued in 1976 that the radiation is purely thermal and carries no imprint of whatever fell in, which destroys information and breaks quantum mechanics. Proposed rescues have all failed somewhere. Stable remnants that hold the information would be produced in unlimited numbers by ordinary physics. Slow leakage, worked out by Page in 1993, reproduces the right entropy curve but demands non-local transfer nobody can describe. Black hole complementarity was broken in 2013 by Almheri, Marolf, Polchinski, and Sully, whose firewall argument showed the assumptions are mutually inconsistent, but a firewall at the horizon violates Einstein's equivalence principle. Hawking conceded his bet to John Preskill in Dublin in 2004 and handed over a baseball encyclopedia. The paradox outlived him. Every black hole is therefore a slow leak, and the leak is where nearly everything ends up. The atoms of every star, every planet, every ocean and library and species that gets swallowed comes back out over 10 to the 67 years as featureless heat at a temperature colder than anything that exists today. When the last black hole finishes evaporating, either the record of everything that fell in is somehow still there, or the past has stopped being true. Which? Slow endings assume the universe stays patient. It might not. Number 7. The Big Rip. Robert Caldwell was doing bookkeeping. Around 2002, cosmologists fitting dark energy were describing it with a single parameter, W, the ratio of its pressure to its energy density, and they routinely bounded the fit at -1, because that is the value a cosmological constant takes, and below it the physics gets disreputable. Caldwell asked what would happen if you simply let the fitter go there. A parameter space audit, nothing more. A cosmological constant is well behaved. At W equals exactly -1, dark energy density stays fixed as space expands. More volume, more dark energy, same density everywhere. Distant galaxies recede, the cosmic web thins out, but gravity keeps winning locally. The Milky Way stays bound. The solar system stays bound. Your body never feels the expansion at all. Push W below -1, and the density climbs as space grows. The repulsion is fed by the expansion it creates. That is a runaway, and runaways have endings with dates on them. Caldwell, Mark Kamiankowski, and Nevin Weinberg published the result in Physical Review Letters in 2003 under the title Phantom Energy and Cosmic Doomsday, and they were specific. Taking W equals -1.5 as a worked example, the end arrives 22 billion years from now. 60 million years before that moment, the Milky Way is torn apart. 3 months before, the solar system unbinds. 30 minutes before, the Earth comes apart. In the final 10 to the -19 seconds, atoms themselves dissociate. The theoretical objections arrived immediately, and none of them closed the case. Phantom energy violates the dominant energy condition, which is the constraint that keeps energy from flowing faster than light. Sean Carroll, Mark Hoffman, and Mark Trodden showed in 2003 that a field with the required negative kinetic energy is catastrophically unstable. The vacuum would decay into phantom particles in ordinary matter almost instantly. The patches proposed since then. Ghost condensates and K-essence models with higher derivative terms and imposed high-energy cutoffs, each by stability, by introducing a scale nobody can measure. And the measurements refuse to settle it. Planck's 2018 results put W at -1.03, plus or minus 0.03, sitting on the forbidden side of the line, by an amount too small to mean anything, and too persistent to ignore. Of everything on this list, this is the only ending that reaches your body directly. Not a slow cooling, not a distant collapse. The space between the atoms in your hand widens faster than the electromagnetic force can pull them back, on a schedule that could in principle be printed. The best fit value of W has hovered just under -1 for more than 20 years now. Statistical noise? Or a result nobody wants to believe? Expansion tearing everything apart has an opposite, and it just came back. Number 6. The big crunch nobody expected to return. Alexander Friedman was solving equations, not forecasting. In 1922, he took Einstein's field equations and worked out the complete family of solutions for a uniform, expanding universe. 3 cases fell out of the algebra. One of them had the expansion slowing, halting, and reversing into total collapse. He published it as mathematics. For most of the 20th century, that solution was the front runner. Then, the sky answered. In 1998, 2 independent teams, the High Z Supernova Search led by Adam Ries and Brian Schmidt, and the Supernova Cosmology Project led by Saul Perlmutter, measured distant type Wea supernovae and found the expansion accelerating. Collapse was finished as a serious idea. The universe was going to expand forever, coasting outward on something nobody could identify. Acceleration only rules out a crunch if dark energy is a constant. If it is a field, it can roll. And a rolling field can pass through zero. Renata Kalash, André Linde, and their collaborators published observational bounds on cosmic doomsday in the Journal of Cosmology and Astroparticle Physics in 2003, showing that a quintessence field on a simple linear potential, fully consistent with every observation available at the time, could reverse the expansion and collapse the universe within about 10 to 20 billion years. In 2022, Cosmin André, Anna Ijas, and Paul Steinhardt published in the Proceedings of the National Academy of Sciences a model in which a rapidly descending quintessence field halts cosmic expansion within roughly 100 million years and completes the collapse in well under 100 billion. Ruling this out turns out to be very hard. Testing it requires measuring how W behaves at high redshift, and type 1a supernovae give out around redshift 2. The era where the field's descent would show up is largely beyond reach. The shape of a quintessence potential is constrained by taste rather than data. A linear potential is exactly as motivated as any alternative. The anthropic escape hatch fails on inspection, since 100 million years is comfortably far away by any human measure, while being nothing on a cosmic clock. Laboratory fifth force experiments limit how quintessence couples to matter, but say nothing about the potential slope. And a crunch may not even be an ending. Steinhardt and Turok's cyclic models turn it into a bounce, though the bounce itself sits in a regime where no one can compute anything. Under this model, the acceleration you were born into is a passing phase, and the far future is not a fading sky, but a brightening one. Galaxies crowding back together, the microwave background blue shifting, the night warming toward day. If dark energy can weaken, there is nothing in the physics that says it stops at zero, so why would it stop at zero? That used to be a fringe scenario. Then, a telescope on Kitt Peak changed the odds. Number 5. The dark energy that appears to be changing. DESI was built to make a map. 5,000 robotic fiber positioners mounted on the 4-meter Mayall telescope at Kitt Peak, each one reconfiguring itself every 20 minutes to catch a different galaxy, assembling the largest three-dimensional survey of the sky ever attempted. The core measurement is unglamorous. Locate the baryon acoustic oscillation scale, a fixed ripple frozen into the distribution of matter, and use it as a ruler at different distances. Standard cosmology bookkeeping. The model being tested had been undefeated since 1998. Dark energy as a cosmological constant, W fixed at -1. Density unchanging. The same in the early universe as today. It fits the microwave background. It fits supernovae. It fits large-scale structure. 6 parameters, 1 universe, no tension worth losing sleep over. The ruler came back wrong. Not wildly wrong. Wrong in a direction. Consistently across redshift bins. Dark energy looked stronger in the past and weaker now. DESI's first data release in April 2024 flagged the preference. The second, in March 2025, drew on more than 14 million galaxies and quasars, and reported that a 2-parameter evolving model was favored over a constant at somewhere between roughly 2.8 and 4. 2 sigma, with the exact figure depending on which supernova compilation you fold in alongside the microwave background. The parameterization being fit is the Chevalier-Pilarski-Linder form, introduced by Michel Chevalier and David Pilarski in 2001, and by Eric Linder in Physical Review Letters in 2003, which describes W as a straight line in the scale factor. That dependence on the supernova sample is the whole argument. Pantheon Plus, Union 3, and the DES 5-year sample give meaningfully different significances from identical DESI data, which is the signature of a systematic rather than a discovery. George Efstathiou argued in a 2024 analysis that small calibration offsets between low redshift and high redshift supernovae can manufacture exactly this signal. The CPL form itself has no physical derivation behind it, and fitting the wrong functional form to real data reliably produces apparent evolution. Neutrino mass is degenerate with the evolution parameter, and some combined fits push the summed neutrino mass to negative values, which is not a thing that exists. And 4 sigma is roughly where the 750 GeV diphoton excess lived in 2015, before it evaporated with more data. If it holds, the ending changed during your lifetime. The fate of everything moved from an eternal, gentle, unremarkable cold drift to something with a calculable finish. And the shift happened in a data release most people never heard about. How many sigma should it take before you change your mind about what happens to everything that exists? Every ending so far comes with a timeline. The next one does not. Number 4. The false vacuum. Sidney Coleman was working a technical problem. In the mid-1970s at Harvard, he wanted a proper method for calculating how a quantum field escapes a local energy minimum when a deeper one exists elsewhere, the field theory version of a ball resting in a dent partway down a hill. It was a formal exercise in semi-classical approximation, the sort of thing that ends up as a chapter in a graduate textbook. The vacuum, in field theory, is just the lowest energy configuration of the fields. Ours has held steady for 13.8 billion years. Every experiment ever performed, every constant ever measured, every chemical bond in your body depends on the fields sitting where they sit. Stability is not usually treated as a question. It is treated as the floor everything else stands on. Coleman found that the field does not tunnel everywhere simultaneously. It nucleates. A bubble of true vacuum appears at a single point, and the bubble wall accelerates outward until it is moving at very nearly the speed of light, and it does not stop. He published Fate of the False Vacuum in Physical Review D in 1977 and in 1980. With Frank DeLuzia, added the gravitational corrections. Then the Higgs boson turned up and made it concrete. Giuseppe Di Grassi and collaborators in 2012, and Dario Buttazzo and colleagues in 2013 calculated the shape of the Higgs potential with the measured mass of 125 GeV and a top quark near 173 GeV, and found a second, deeper minimum opening up around 10 to the 11 GeV. Our vacuum is metastable, and it sits almost precisely on the dividing line between stable and unstable. Anders Andreasen, William Frost, and Matthew Schwartz computed the resulting lifetime in Physical Review D in 2018 and got something on the order of 10 to the 139 years. Comfortable, until you read the error budget. That lifetime is exquisitely sensitive to the top quark mass, move it by a fraction of a GeV, and the conclusion flips between metastable and stable. The top mass itself is not cleanly measured. What the LHC extracts is a parameter defined inside Monte Carlo simulations, whose relationship to the theoretical pole mass is still argued about. Any new physics above 10 to the 11 GeV reshapes the potential completely, and we have no experimental access to that scale. Gravitational corrections can suppress or enhance the rate depending on Planck scale terms nobody can calculate. Ruth Gregory, Ian Moss, and Philip Berta showed in 2015 that small black holes can act as nucleation seeds and accelerate the process by many orders of magnitude. Every correction is large, and none point the same way. This is the one item with no warning built in. A bubble expanding at light speed outruns every possible signal of its own approach, which means it could have nucleated a billion light years away a billion years ago, and there would be no photon, no tremor, no anomaly, nothing at all until it is already here. What does it mean to live somewhere whose continued existence is a measurement of one quark's mass, accurate to a fraction of a GeV? Assume nothing ends the universe. That turns out to be the more disturbing case. Number 3. Poincaré recurrence and the Boltzmann brain. Henri Poincaré was competing for a prize. In 1890, he was working on the three-body problem for a competition sponsored by King Oscar II of Sweden, trying to determine whether the solar system is stable. In the middle of that analysis, he proved a general theorem about bounded systems with conserved energy, given enough time. Such a system returns arbitrarily close to any configuration it has ever occupied. He was doing celestial mechanics. He had described a property of eternity. The second law is the most reliable statement in physics. Entropy increases. Eggs break and do not unbreak, heat flows from hot to cold and never back, and the whole difference between past and future, the reason memory points one way, rests on that gradient. It has never once been observed to fail. Recurrence says the gradient is local. Wait long enough, and the fluctuations run the other way. the egg reassembles, not as a miracle, as arithmetic. Ludwig Boltzmann raised the possibility in an 1895 letter to Nature, crediting the idea to his former assistant Dr. Schwetz. Perhaps the ordered region we live in is a rare downward fluctuation in an otherwise dead universe. Arthur Eddington dismantled the naive version in Nature in 1931, pointing out that if a fluctuation can produce an observer, then by overwhelming probability, it produces the smallest possible observer with fabricated memories rather than an entire coherent world. The modern version arrived in 2002, when Lisa Dyson, Matthew Kleben, and Leonard Susskind published disturbing implications of a cosmological constant in the Journal of High Energy Physics. A universe with positive dark energy behaves like a sealed thermal box with a de Sitter entropy near 10 to the 122, and its recurrence time is roughly erased to that number of years. Over that span, fluctuation observers outnumber ordinary ones without limit. The escape routes all cost something. End the universe before recurrence has time to matter. That is one of Steinhardt and Turok's stated motivations, and it requires new physics. Let dark energy decay, so de Sitter space is only a phase. Argue that de Sitter space is not genuinely a closed box because of the horizon. A position Susskind himself has taken from more than one side. Sean Carroll's 2017 argument runs differently. Any theory predicting that you are probably a fluctuation is cognitively unstable, because the reasoning that led you to the theory would itself be a random product. That is a decisive reason not to believe it. It is not a reason it is false, which makes the measure problem personal rather than academic. If most beings holding your exact memories in the full history of the universe are momentary assemblies of noise, then your childhood is not a fact you have access to. It is a probability estimate. What evidence could you collect that would rule out having been assembled 5 seconds ago, complete with the memory of collecting it? Set aside the exotic scenarios. The mainstream one is not gentler. Number 2. Heat death and maximum entropy. William Thomson was trying to improve engines. In 1852, in Glasgow, he was working through the practical question of why a steam engine cannot recover all the heat it puts in, an industrial problem with money attached. He wrote it up as a short paper, and almost as an aside, generalized the principle from the engine to everything. The great achievement of 19th century physics was conservation. Energy is never created and never destroyed, it only changes form. Burn coal, and the chemical energy becomes heat and motion and light, all of it accounted for, none of it lost. Nothing ever goes missing from the ledger. Conserved, yes. Usable, no. Every real process degrades energy into a more scattered form, and scattered energy cannot drive anything. Extend that to the whole universe, and you get a cosmos still holding every joule it ever had, unable to do a single thing with any of it. Thomson's paper was titled On a Universal Tendency in Nature to the Dissipation of Mechanical Energy. Hermann von Helmholtz gave the endpoint its name, the Ermitod, the heat death, in a public lecture at Nigsberg in 1854. Rudolf Clausius compressed the whole thing in 1865 into 2 clauses. The universe's energy holds constant, while its entropy climbs toward a ceiling. The modern accounting is due to Chas Egan and Charles Lineweaver in the Astrophysical Journal in 2010, who recalculated the entropy of the observable universe at roughly 3 times 10 to the 104 in units of Boltzmann's constant, around 100 times larger than the accepted figure before them, with supermassive black holes holding essentially all of it. The clean picture starts breaking as soon as gravity enters. Self-gravitating systems have negative heat capacity, lose energy, and they get hotter, which means they never settle into equilibrium the way a gas in a sealed box does. In an expanding universe, the maximum possible entropy may grow faster than the actual entropy, in which case there is no ceiling to reach, and heat death never arrives in the classical sense. Freeman Dyson argued in 1979 that life could survive indefinitely by slowing its metabolism to match the cooling. Lawrence Krauss and Glenn Starkman showed in the Astrophysical Journal in 2000 that accelerating expansion caps the total energy any observer can ever gather, which breaks the scheme. And a de Sitter horizon has its own fixed temperature near 10 to the minus 30 Kelvin, so the true endpoint may be equilibrium with a horizon, a different state, obeying different rules that nobody has fully worked out. Bring that down to the scale of a room. A heartbeat, a held note, a sentence finishing, each one is a temporary difference between two places, permitted only because the universe has not yet finished flattening out. What is a law of physics worth in a universe where nothing ever happens again? Which raises the question this whole list has been circling. Number 1. The expiration date on meaning itself. Rolf Landauer was answering to IBM. In 1961, at the Thomas J. Watson Research Center, he was asked a corporate engineering question with a very practical edge. What is the absolute minimum energy a computation can cost? Chip designers wanted a floor to aim at. Landauer went looking for the number. The expected answer was 0. Information looked abstract. A bit is a pattern, not a substance. And shuffling patterns around ought to be free in principle, limited only by how well you build the hardware. Logic was supposed to be independent of physics. Erasure has a price. Landauer proved that destroying one bit of information costs at minimum kT times the natural log of 2 in energy, released as heat. The number is small. It is not 0, and it never can be. The paper appeared in the IBM Journal of Research and Development in 1961, and its critical feature is the T. The colder you run, the cheaper each operation becomes. Freeman Dyson built an entire eternity out of that clause in Reviews of Modern Physics in 1979, in a paper called Time Without End. His argument was that an intelligence which cools as the universe cools, and hibernates between thoughts to shed waste heat, can execute an infinite number of thoughts on a finite total energy budget. Subjective immortality on a fixed allowance. That result stood for 21 years, until Lawrence Krauss and Glenn Starkman published in the Astrophysical Journal in 2000, and showed that in an accelerating universe, the de Sitter horizon imposes a floor temperature and a hard limit on total accessible energy, and the infinite thought budget collapses to a finite one. The rescue attempts are all real and all fail somewhere. Reversible computing, which Charles Bennett formalized in 1973, avoids erasure entirely, but every physical system leaks, and correcting the resulting errors requires erasing, which reinstates the cost. Store your memory in larger and larger structures, and expansion pulls them apart faster than you can assemble them. Live off black holes. And Page's evaporation rates cap the available power while the last supermassive hole is gone by 10 to the 100 years. Escape into a daughter universe, and you are relying on physics with no experimental support of any kind. Underneath all of it sits Bekenstein's 1981 bound, which limits how much information a finite region of space can contain at all. And the erasure has already started. Krauss and Robert Scharrer showed in 2007 that observers 100 billion years from now will look out at a single isolated galaxy, no other galaxies, no redshift, no microwave background, and derive, from flawless measurements honestly performed, an entirely false picture of the universe. You know what you know because you were born early enough for the evidence to still be here. If the universe eventually forgets that it ever had a history, was any of this ever recorded, or only borrowed? 10 endings, and not one of them comes from the frontier of our ignorance. Heat death falls out of thermodynamics. The rip falls out of the equation of state we fit every year. Vacuum decay falls out of the Higgs mass we measured and celebrated. Boltzmann brains fall out of the cosmological constant we discovered in 1998. These are not gaps in the theory, they are the theory, followed honestly to the end, refusing to give us the ending we wanted. The universe is not confused about what it is doing. We are the ones who assumed permanence was the default, and nothing in the physics ever agreed. If you want to see more videos like this, click the video on screen now.